All right, let's jump right into this explainer. Imagine, just for a second, the sheer, absolutely terrifying physical forces at play on a modern drill ship. We talk a lot about how these incredible vessels hold their position in rough seas, or how they drive a drill bit thousands of feet beneath the ocean floor. But today we're tackling a high-stakes engineering challenge where failure literally isn't an option. Because if you get this wrong, you either drop the drill string or you snap it completely. Today, we're dissecting the active heave drawworks braking system of the GF 12,000 drill ship.
So, hit the brakes for a second and just look at this number. 1,250. On the GF 12,000, that is the maximum rated load, in short tons, of the main well's active heave drawworks, or AHD for short. To put that massive number into perspective, that is the equivalent weight of about 6 Boeing 747s. Just picture all that weight, a colossal string of solid steel pipe descending rapidly into the dark depths of the ocean. Gravity's just pulling it down with terrifying momentum, and at some point, you have to stop it, exactly on target, and you have to do it without completely destroying your own equipment.
Which obviously brings us to the million-dollar question. How on earth do you actually do that? Stopping a moving object that heavy is nothing like hitting the brakes on your bike or even your car. A drill string in motion carries an absolutely enormous amount of kinetic energy, and the laws of physics are pretty stubborn. That energy has to go somewhere. If you just try to clamp down on it using traditional mechanical friction brakes, you generate so much pure heat that you would literally burn the brakes right up. Or worse, the sudden violent jerk would snap the wire line completely, and just like that, 1,250 tons of steel is plummeting to the ocean floor in a catastrophic, uncontrolled drop.
But the brilliant engineered solution to this massive problem? Well, it's actually probably sitting in your driveway right now if you own a hybrid or electric vehicle. We are talking about regenerative braking. It's crazy to think about, but the GF 12,000 uses the exact same foundational technology as a standard 1.5-ton hybrid car. It's just scaled up exponentially to handle a 1,250 short-ton drill string. Okay, let's break down exactly how this works, because it's super clever. Instead of just burning off all that kinetic momentum as useless, dangerous heat, the system uses the very same motors that drive the drawworks. But it uses them in reverse. As the drill string descends and needs to slow down, the sheer momentum of the spinning drawworks drum actually spins the motors. In an instant, these motors flip their function. They stop consuming electricity and instantly become massive generators. They capture the drill string's kinetic energy and convert it right back into electrical energy. That electricity is then safely fed directly back into the ship's electrical grid, or, if needed, dissipated through a resistor bank. Not only does this save a ton of wear and tear, but it smoothly, seamlessly controls the string's deceleration. No sudden jerks, no snapped lines.
So let's take a look at the specific hardware making this happen in the AHD 1250-9000 and its counterpart, the AHD 1000-6900 drawworks systems. You've got these massive GE AC drive motors doing the heavy lifting and the heavy braking. But controlling the stop is really only half the battle, right? You also have to monitor the tension on the line. That brings us to the deadline anchors, which are fitted with compression load cells, and the drill line storage reels that hold all your spare wire line. Now, because this regenerative braking is electronically modulated in real time, rather than just mechanically applied like yanking a handbrake, it gives the operators microscopic precision. They can stop a multi-hundred-ton string exactly at a target depth, zero overshooting, and absolutely no violent jerking.
But here's the catch. You literally cannot safely stop a load if you don't know exactly what that load is. Enter what I like to call the fisherman's scale of the drill ship. The massive wire line that holds all this weight has one fixed end that's tied down incredibly securely. We call this the deadline anchor. And built right into this anchor is our most critical measuring tool.
This part brilliantly illustrates the difference between just hoping for the best and actually knowing for sure. Back in the day, or on older, less sophisticated rigs, operators might have to kind of guess the weight based on indirect tension or just by feeling out how the equipment was behaving. Not here. No way. The compression load cell on the deadline anchor acts exactly like a permanently built-in digital fish scale. Instead of estimating, the operators are getting an independent, direct, continuous, real-time number. It shows them exactly how much weight is hanging off that drawworks practically down to the pound.
Which brings us to the hidden danger of braking. It's captured perfectly by this formula right here. Dynamic line tension equals the static string weight plus the mass multiplied by deceleration. Now, what is this actually telling us? It means the weight of the pipe just hanging there, the static weight, is only part of the story. The absolute second you hit the brakes, you introduce deceleration, and the faster you try to stop, the higher that deceleration multiplier gets.
A sudden stop takes that massive static weight and adds a huge dynamic load spike right on top of it. And guys, this dynamic tension is exactly what snaps wire lines.
To really visualize this, think of your static string weight as your baseline. It's heavy, sure, but it's well within the safety limits of the wire line. But then, say you slam on the brakes. Boom! You introduce the force generated by mass times deceleration. Suddenly, you are hit with the terrifying reality of total dynamic line tension. That spike you see? That is the string's momentum violently pulling against the stopping force. This is precisely why the deadline load cell is there, to catch these exact spikes in real time. And it completely highlights why the smooth, electronically controlled deceleration of regenerative braking is so absolutely vital. It's all about keeping that deceleration multiplier as small as possible.
But as we all know, things in the real world don't always go perfectly to plan. So there is an absolute, non-negotiable rule of thumb on a drill ship. Any sudden, unplanned deceleration event, like an uncontrolled emergency stop, triggers an immediate mandatory inspection of the wireline and the deadline anchor. Why? Because that dynamic overload spike we just looked at is the most common precursor to wireline fatigue failure. The metal in the wireline actually remembers that stress. If you just ignore a dynamic overload spike, the very next time you pick up a heavy load, that line might just give out entirely.
Now, we do have to talk about limits. Regenerative braking is absolutely incredible for normal operations. It absorbs the energy, it's buttery smooth, it's super precise. But its capacity is not unlimited. You are feeding massive amounts of electricity back into the ship's grid. If a major emergency demands a deceleration that's faster than the motors and the electrical system can absorb, well, you've exceeded your emergency limits. The ship's grid simply cannot take the juice. And when that happens, you desperately need a backup plan.
And that backup plan is the ultimate analog failsafe, the emergency sequence. Step 1. The regenerative limit is reached. The grid is maxed out. Step 2. Because relying solely on the electrical grid during an emergency stop is a critical design failure point, the massive mechanical friction brakes immediately engage. They physically clamp down to take over. Now, it is rough, it generates a massive amount of heat, and it might even spike that dynamic tension we talked about, but it does its job. It stops the drop. Then, step 3 happens after the dust settles. Because of the intense wear and tear from these emergency loads, the crew has to use that drill line storage reel we mentioned earlier. They do what's called a line slip and cut maintenance, feeding fresh wire line into the system and cutting off the fatigued, stressed section. That guarantees the drawworks is safe to lift another day.
Which kind of leaves us with this final provocative thought. In a world that is increasingly dominated by software, digital sensors, and complex electrical systems, like our highly advanced regenerative braking, is trusting a single primary system without a raw, analog, mechanical backup a catastrophic design flaw? On the GF12000, the engineers decided they were absolutely not going to risk finding out. They balanced 1,250 tons of falling kinetic energy on an invisible cushion of electromagnetism, sure, but they always keep a pair of massive, old-school steel friction brakes waiting in the wings, just in case. It's just a fascinating balance of massive physical forces and incredibly intricate control. Anyway, that wraps up our look at the Drawworks braking systems. Keep exploring, keep questioning how these massive machines work, and we'll see you in the next explainer.